Hello, I'm Bogyang from Donggu University DTM Lab. The paper I will review is Translate Patent Vacancies into Human-Readable Text, Identifying Technology Opportunities with Text Embedding Inversion. First, this is the bibliographic information for the paper. This paper was published in the journal Advanced Engineering Informatics in 2025. The contents are the same as the structure of the paper. This is introduction. In the current rapidly evolving technological landscape, the ability to innovate continuously and capitalize on emerging technological opportunities has become critical for corporate survival and growth. So researchers have extensively explored future technological opportunities within the vacant area of patent map. However, precisely defining and interpreting these patent vacancies still remain a significant challenge in the field. Although a GTM-based patent map approach has been proposed to overcome this limitation, it still falls short in that patent vacancies can only be described at the keyword level. So this study purposes a novel approach to identifying and specifying technology opportunity for a patent map, which utilizes the embedding inversion model. By employing this model, vacancies identified in patent map can be transformed into human-readable and understandable text rather than mere keyword. Next is the related work. First is TOD with patent mapping. DFM systemically maps technological elements to the function they support, and by identifying cells with low patent counts, it aims to accurately identify potential technology vacancies. But there is a limitation in that highly specific technological insight cannot be derived for the identified vacant cell. The link prediction approach seeks to identify connection among keyword or patent in network construct for patent data, thereby revealing potential opportunity by exposing latent or previously unnoticed relationship. It may struggle to pinpoint entirely novel domain, the so-called unknown that are absent from today's market or technology landscape. GTM allowed more precise inference about technological vacancies by presenting the keyword that constitute patent vacancies. However, GTM-based approach, while an improvement, still primarily represent vacancies as that of keyword, limiting their direction conversion into a fully human-readable narrative format. So the development of a systemic and objective method for defining patent vacancies remain a significant challenge. To overcome this limitation, this study employed the embedding inversion method to transform patent vacancies into a form that can be clearly comprehended by human. Second is density estimation for patent analysis. Understanding the distribution and concentration of patent within a technological landscape is essential for identifying both areas of intense activity and untapped opportunities. To visualization this pattern and identify technological hotspot, kernel density estimation has become a widely used method in patent analysis. KDE-based heatmap help visualization the spatial distribution of patent, highlighting both core and peripheral area in a technological domain. Patent density quantification through KDE enable objective identification of hotspot, which is variable for competitive intelligence and understanding technology trends. Cold spot can indicate potential technology vacancies or unexplored opportunities. Third is embedding inversion. Embedding inversion is a technique for restoring high-dimensional embedding to their original data form. One of the most advanced model in this area is back-to-text, which reconstruct the original text through the following iterative refinement process. First, it generates an initial text hypothesis, then it refines this hypothesis by calculation the difference between the current embedding and the target embedding. Finally, the model converts the embedding vector into a sequence suitable for transformer input using a transformer-based encoder-decoder architecture and a multi-layer perceptron. This process allows back-to-text to recover current and highly accurate text representation for fewer embedding vector. Next is the proposed approach. This study proceeds according to the process illustrated in Figure 2. It proposed an approach that generates a patent map based on patent data, identifying patent vacancies within the map and extract corresponding text to convert them into a human-readable form. The process proceeds as follows. First, step 1 is patent embedding. First, the patent abstracts are transformed into 1536 dimensional embedding using a text embedding model. In this step, OpenAI text embedding ADA2 model is adopted due to its direct compatibility with the back-to-text model used for embedding inversion. Step 2 is autoencoder training. The high-dimensional embedding of the transform patent abstract are used to train an autoencoder. This neural network model is designed to compress input data into a lower dimensional space and then reconstruct it back to its original form. In the training process, the autoencoder is optimized to compress and reconstruct the patent abstract data by minimizing the difference between the encoder's input and the decoder's output. Through this process, the model learns and captures the salient feature of the input data. Step 3 is dimensionality reduction and density estimation. By using the encoder of a previously trained autoencoder, high-dimensional embedding are compressed into two-dimensional representation, generation two-dimensional coordinate for patent abstract and forming the basis of the patent map. The two-dimensional spaces that divide into cells of a specific size and the patent density within each cell is calculated. Next, KDE is applied to estimate the technological density and identify both high density and low density region. Step 4 is vacancy identification. In this study, a vacancy is defined as a region on the patent map where no data point exists within a given cell as illustrated in Figure 3. Once a cell is identified as a vacancy, this study designates its centralized as the representative coordinate of that vacancy. Step 5 is dimensionality reconstruction and embedding inversion. First, the two-dimensional vacancy coordinate identified earlier are reconstructed into their original 1536 dimensional space using the trained autoencoder's decoder, and then using the back-to-text model, high-dimensional embedding are converted into human-readable text. This entire Step 5 process operates as an automated pipeline for once the model are trained and the vacancy coordinates are identified. Next is the case study. To demonstrate the proposed approach, this study conducts a case study on patent-related LiDAR technology. A total of 17,616 data records were collected from the USPTO based on IPC code, keyword, and publication date. Then the abstract of the collected patent were converted into 1,576 dimensional vector using the text embedding A.2 model. In step 2, an autoencoder is trained using the generate patent embedding. During this process, the MSE is implied as the loss function to measure the difference between the input data and the reconstruct output. Through this approach, and effectively compressed two-dimensional representation was produced while preserving the essential feature of the LiDAR patent data. In step 3, KDE is applied to the two-dimensional representation to generate the final patent map as shown in figure 4. The study first identified patent vacancy in the three relatively high density area. Figure 5 presents a visual representation of the identified patent vacancies in each of the three zones. Then in step 5, this study converts in the identified patent vacancies in the LiDAR technology domain into high-dimensional embedding. At this stage, the decoder for the autoencoder trained in step 2 was used. Next, the embedding inversion model back-to-text were employed to transform these high-dimensional embedding back into their original data format. As an example, table 1 presents the vacancy abstract of the three selected examples V1, V2, and V3, which are specific in figure 5. Next, the proposed approach was evaluated for its practical applicability in discovering future technology opportunities. The 5,377 patent abstract of the out-of-sample dataset were embedded in the same way and overlaid on the patent map in figure 4. Then the technical content of the real patent were compared with that of the corresponding vacancy abstract, both in a quantitative and in a qualitative way. As a result, many of the identified vacancy zones were later filled by actual patent, and the generate vacancy abstract exhibit high similarity to the real patent abstract, both quantitatively and qualitatively. Next is the conclusion. This study proposed the first approach to translate patent vacancies into human-readable text and identify technology opportunity by integrating text embedding, autoencoder density estimation, and embedding inversion. It also demonstrates the potential for practical applications such as corporate R&D, stretch, and competitor analysis. However, the study has limitations. The generated text tend to be short, limiting their technical depth, and long-term validation is required to determine whether the identified vacancies truly represent future technology opportunities.